All right, hello everyone. As I said, the recording I was making today during class was lost due to a computer issue, so I'm just hanging around after school and doing a quick recording of the examples that we covered in this lesson. This is lesson 20.2.2. We're going to continue to work on trigonometric ratios using the coordinate grid. I'll just remind you before we get started here that when you talk about trigonometric ratios on the coordinate grid, we have different definitions of how to calculate the sine of an angle, the cosine of an angle, and the tangent of the angle. And those definitions are in terms of x, y, and r, where x and y are the coordinate pair that define a point on the terminal arm of the rotation angle. This was from the last lesson. And r is the distance from the origin to that point. So what we ended up doing in the previous lesson was we said, let's dispense with the idea of opposite, adjacent, and hypotenuse, because when you look at rotation angles, the angle that we're talking about is not an angle inside of a triangle. So it makes no sense to talk about opposite, adjacent, or hypotenuse. We equate the opposite side in the traditional definition of trigonometric ratios. We equate the opposite side now to be equal to the y coordinate, the adjacent side is the x coordinate, and the hypotenuse now becomes r, which is the distance from the origin to the point on the terminal arm. So that's where those three definitions come from that you're looking at on the right-hand side of your screen. And of course, the relationship between x, y, and r is a Pythagorean relationship. X squared plus y squared is equal to r squared. So what we are doing today is continuing to work with those definitions. Just to get something out of the way, we are not going to be dealing with in this lesson this objective. And that means when you get to example 7 in the handout, we're not worrying about it. What this lesson boils down to is two topics, really. Finding the trigonometric ratio for what we call quadrantal angles. And I will explain to you what a quadrantal angle is in a minute or two. And then the remainder of the lesson, even though I've got it broken down in my notes for my purpose, the remainder of the lesson is finding rotation angles. So we're going to be finding the values of a rotation angle. Whether we're finding the approximate value, which means we're going to express the rotation angle in decimal form, or whether we're finding the exact value, which means we will get a precise angle like 30 degrees or 210 degrees. Whether we're going to get a decimal angle or an exact value angle that has no decimals doesn't change how we solve these problems. So what's highlighted in yellow is the first objective of the lesson, and what's highlighted in blue is really basically the second objective. Let's deal with the first objective, which is finding trigonometric ratios of quadrantal angles. Example 1 says we're going to use the definitions of the three primary trigonometric ratios, which are sine of theta, cos of theta, and tan of theta. We're going to use those definitions of those ratios to determine the sine of 0 degrees, and the sine of 90 degrees, and the sine of 180 degrees, and the sine of 270 degrees. And the same with the cosine, and the same with the tangent. So off on the side here, I'm simply going to remind you that the sine of an angle is equal to y over r. The cosine of an angle is equal to x over r. And the tangent of an angle is equal to y over x. Let's focus to begin with on 0 degrees. 0 degrees is a very uninteresting angle, but in terms of coordinate trigonometry, what it looks like is that we have a terminal arm on the positive x-axis. So that's 0 degrees. And we need to pick a point on this terminal arm to talk about x and y. So I'm just going to label that point x comma y. And I'm also going to indicate on this diagram what r is. R is the distance from the origin to that point. And one of the things you'll note is that when you have a point on the x-axis, the y-coordinate is 0. So in this particular case, we're talking about a y-coordinate of 0, which means that the sine of 0 degrees is going to have a value of 0. Because, and this is just my scrap paper here, sine of 0 degrees is the y-coordinate at that point over r, but the y-coordinate is 0, so we have sine of 0 degrees equals 0 over, well, quite frankly, I couldn't be bothered to worry about what the value of r is. If y is 0, y divided by r would be 0 divided by r, and 0 divided by any non-zero number will be 0. Similarly, tangent of 0 degrees is going to be 0 as well. And again, the work that I'm showing at the bottom of the screen is going to be erased. This is just what I consider my scrap paper. Tangent of 0 degrees is the y-coordinate at that point over the x-coordinate, but the y-coordinate at 0 degrees is 0, so 0 divided by whatever the x-coordinate is going to be 0. Well, now let's talk about the cosine of 0 degrees. The cosine of 0 degrees, since the cosine of any angle is x over r, the cosine of 0 degrees will be defined by the x-coordinate on that diagram divided by the value of r. But one of the things you'll notice is that in this diagram right here that I'm indicating, r is the x-coordinate. I mean, I can certainly give you some specific numbers here. Let's imagine that that point is at 12, 0. And I said to you, that point is at 12, 0. What is this distance? You would say, well, that distance is 12. So the x-coordinate of that point is 12. The value of r is 12. And it doesn't matter which particular point on the x-axis we choose. What we discover is that the x-coordinate and r will be equal to each other. So essentially what you have is x over x, and that's going to give you 1. Now what we did in class is we confirmed this. First of all, let me clear my scrap workspace. We confirmed this on the calculator, and this is something we actually did in class in previous lessons. We took the sine of 0 degrees, make sure you were in degree mode. I am, you get 0. We took the cosine of 0 degrees, you get 1. We took the tangent of 0 degrees, and we got 0. So let's do the same thing for 90 degrees that we did for 0 degrees. If I were to take a look at what a rotation angle looks like at 90 degrees in terms of the terminal arm, 90 degrees means we're rotating from the positive x-axis 90 degrees. So what we have is a point on the terminal arm, which has an x-coordinate and a y-coordinate, and we have this distance in here from the origin to that point as being r. Well, one of the things you need to note is that the x-coordinate at 90 degrees will be 0. Any point that's on the y-axis has an x-coordinate of 0. And what that means is that since cosine of theta is x over r, it means that cosine of 90 degrees will be 0 over r, which means cosine of 90 degrees is 0. If we take a look at sine of 90 degrees, well, sine of 90 degrees is going to be the y-coordinate over r, and the y-coordinate is some number that's equal to the value of r. Again, I can put specific numbers on here, just like I did last time. At 0 degrees, I can say that this point is at 0, 10. So the y-coordinate is 10, and this distance, which is r, is 10. So we would have 10 over 10, which is 1. So the sine of 90 degrees is 1. When we start to look at tangent, things get a little more interesting. Since tangent of a rotation angle any rotation angle is y over x, tangent at 90 degrees will be y over x. And in our diagram, I've got y equals 10, but the fact that it's 10 is unimportant. In our diagram that I've drawn there, the y-coordinate is some number. What's important is it's divided by the x-coordinate, which is 0. And without going into a deep explanation, which I did in class, when you divide by 0, you get an undefined value. So y divided by 0 is not defined. We talked about in class the fact that you can view it as being infinity, but at this level what we want to say is simply it's undefined. I won't spend video time doing this, but if you take the sine of 90 degrees on your calculator, and you can certainly pause the video right now and do it, you will get 1. If you try to take the cosine of 0 on your calculator, pardon me, I'm going to back up. If you take the cosine of 90 degrees on your calculator, you're going to get 0. And if you try to take the tangent of 90 degrees, you will get an error on your calculator. We take a look at 180. 180 degrees has a terminal arm here. Let's cut to the chase and choose a specific ordered pair here of -4, 0. If that's at -4, 0, r is 4. And you can see that when you try to take the sine of 180 or the tangent of 180, you're going to be taking y divided by r for sine, and that will be 0 divided by 4 in our example, but that's going to be 0. When you try to take the tangent of 180 with our specific numbers, you're going to take the y-coordinate, which is 0, divided by the x-coordinate, which is -4. You will still get 0. If you were asked to take the cosine at 180 degrees using the numbers we have would be x over r, which would be -4 over 4. But in the end, it doesn't matter what those numbers are. They are going to be equal but opposite, which means cosine is -1. Because I'm not exactly in a position here where I have a lot of time, I'm just looking at the clock, I'm just going to briefly, very briefly, talk about the remaining column and tell you that if you want, you can reproduce the results by continuing to draw a terminal arm that is at 270 degrees, which would look like this, by picking a specific point on the terminal arm and running through the same logic that we did with 0 degrees, 90 degrees, and 180 degrees. But what you are going to discover is the sine of 270 is -1, the cosine of 270 is 0, and the tangent of 270 is undefined. Now, before we go on to what I would call the most important part of today's lesson, I think it's important that you understand this logic that we've used to come up with the exact trigonometric ratios of these special, what we call quadrantal angles, is not something that you would encounter on an exam. It's not something you're going to encounter on your practice today. It's something that I'm teaching you now so that when we get to Math 30-1, you're in a better position to handle the trigonometry there. All right, let's move on. Let's take a look at the remaining examples, which are going to be examples 5 and 6. And what we're doing in questions 5 and 6 is we're really solving an equation. We have this equation, sine of theta is equal to this number, -0.2595. And what we want to do is find theta. It says, determine the measure of theta. So another way I could answer this question is solve for theta. But we do have a condition here, and that the condition is 0 degrees is less than or equal to theta, which is less than or equal to, which is just less than 360 degrees. And this is a fancy way of saying we want to find all of the angles for theta that make that equation true. And the angle can be any angle between 0 and 360 as long as it makes it true. So there are a series of steps that you need to follow to solve these trigonometric equations, and it's important that you follow along very carefully on your calculator. Last year, all of the angles that we dealt with were less than 90 degrees. And if you had an equation last year in Math 10 that said sine of theta equals, this is a different question, I'm just taking us back in time, sine of theta equals 0.8632, and you were asked to find theta, what you would do is you would say theta is equal to the inverse sine of that number. And what you would do on your calculator to access the inverse sine function is you would take second sine. So I hit the second key and then the sine key and put 0.8632 there, and the angle would be 59.7 degrees. Now, what I'm going to tell you is that whenever you're dealing with angles in this unit, angles that are rotation angles, the first thing to note is when you do that, you're not going to get theta. What you are going to get is the reference angle. So it's the reference angle that's equal to the inverse sine. Now, don't do any calculating just yet, because there's one other point that I want to make. The reference angle is the inverse sine, and it will be the inverse sine of 0.2595. This negative, I never want you to use this negative when you go second sine. Trust me on that. If you do, you're going to get weird results depending on whether it's sine or cosine or tangent. And that's not what we want to do. We want to do it so that regardless of whether it's sine, cosine, or tangent, we do it the same way all the time. So this is the reference angle. If the sine is equal to a negative, or the cosine is equal to a negative, or the tangent is equal to a negative, you do not include the negative when you find the reference angle. All right, so we're going to take our calculator and take the inverse sine of 0.2595, and we get to the nearest tenth, 15.0 degrees. Then what you're going to do is look at the original question, and I'll highlight the original question for you. The original question is this. And you ask yourself which quadrants the rotation angle could be in. And now what we're going to do is we're going to notice that in this equation, it says that sine of theta is a positive, in this question it says sine of theta is a negative number. Sine of theta is negative 0.2595. And we think about that, and we also think about the fact that sine of theta is defined by being y over r. And we ask ourselves, if sine of theta is negative, what does that tell us about y? Well, the only way sine of theta can be negative is if y is negative, because r is always positive. This is what we've learned over the past couple of days. And that means that out of this thought comes the idea that theta could be in quadrant 3, where y is negative, or theta could be in quadrant 4, where y is negative. And we draw that reference angle of 15 degrees in quadrant 3, and we draw the reference angle of 15 degrees in quadrant 4. Remember what I've told you about reference angles. They don't have a direction. So when I indicate that this is the reference angle, it's not clockwise or counterclockwise. It's just an angle. Now, don't forget the question said solve for theta. Theta is not a reference angle. Theta is a rotation angle. So we're trying to find theta. Theta for the first diagram would be indicated by this green arc, and for the second diagram would be indicated by that green arc. And from the previous couple of lessons, you should know that on the diagram on the left, we can find theta by taking 180 degrees plus 15 degrees and getting 195 degrees. We were asked to round our answers to the nearest tenth, and it works out to 195.0 degrees. Our other angle, this was the first rotation angle, our second rotation angle would be equal to 360 degrees minus 15 degrees, which by my count gives 345.0 degrees. So if we stop for a second and take a look at all of the steps involved here, your first step is basically to find a reference angle. That's what you do first. Your second step is to determine which two quadrants those are in and draw those reference angles in those quadrants. And your final step is to use those diagrams to determine the rotation angles. So let's try now 5b. We have tangent of theta equals 1.2663. So let's find the reference angle by using our calculator and taking the inverse tangent of 1.2663. It's not negative, so we don't have to worry about forgetting about the negative in our calculation. But again, if the tangent were negative, we wouldn't put the negative into our calculator when we do the reference angle calculation. So what do I get for a reference angle? Let's see, inverse tan of 1.2663 gives me 51.7 degrees. That's kind of step one. Step two is to say which two quadrants. So now what we're doing is we're looking at the fact that tangent is positive. If tangent of theta is positive, and we also know that tangent of theta is y over x, there's actually two possibilities here. Y can be positive and x can be positive. So when you divide y by x, you'll get the positive that we want. Or y could be negative and x could be negative, in which case when you divide the negative y by the negative x, you get a positive for tangent. So you ask yourself, in which quadrant are x and y both positive, and that's quadrant 1. In which quadrant are x and y both negative, and that's quadrant 3. And now we're just about ready to finish this problem. We sketch a rotation angle showing a terminal arm in quadrant 1 with a reference angle of 51.7 degrees. And we do the same thing in quadrant 3. We recognize that the rotation angle is an angle counterclockwise from the positive x-axis to the arm, so we can draw those. And then we ask ourselves how we find theta from each of those diagrams. In the case of the arm terminating in quadrant 1, whatever the reference angle is, that's the rotation angle. And I will remind you again that when we write theta and we don't put any subscript or label on it, we mean rotation. If, however, it is in quadrant 3, the rotation angle can be found by taking 180 degrees and adding that additional reference angle of 51.7. So 180 plus 51.7, I believe, gives 231.7. And that's example B. C, cosine of theta equals -2/5. So you should be getting to be kind of a seasoned veteran at this by the time we get to C. The first thing to do is to find the reference angle, which will be found by taking the inverse cosine of 2/5. Remember, you do not include the negative in your reference angle calculation. So I take the inverse cosine of 2/5 and get 66.4 degrees. So theta reference is 66.4 degrees. I now look at the fact that cosine was negative, and I ask myself, where is cosine of an angle negative? Well, thinking about this, cosine of an angle is equal to x over r. R is always positive. So the only way we can get a negative cosine is if x is negative. Where is x negative? Well, x is negative over here, which is quadrant 2, and x is also negative over here, which is quadrant 3. So I draw or sketch a terminal arm in quadrant 2 and a terminal arm in quadrant 3 with a reference angle of 66.4 degrees for each of them. Then I figure out what the rotation angle is, which would be that. And I figure out what this rotation angle would be, which would be this. So remember, the number that pops out of your calculator is not the answer to the question. It's only the reference angle. If it's in quadrant 2, what I'm going to need to do is take 180 degrees and subtract that 66.4. And I believe that's going to give 113.6 degrees. And if it's in quadrant 3, which we've already done this calculation a number of times, I'm going to have to take, I guess I should write up here for you, this is 180 minus 66.4. Over here, it's going to be 180 plus 66.4, which is 246.4 degrees. Feel free to check those numbers on your calculator. I just don't want to pull up the calculator at this point to find them. I think they're correct. Now let's take a look at the last example, solve for theta. It's the same kind of question. We're going to find the reference angle here by taking the inverse sine of root 3 over 2. And I'm going to ask you to find it right now. You pause the video, find the reference angle, and then start the video again. You should have got for a reference angle 60 degrees. And what makes the questions in example 6 different than the questions in example 5 is you should have got exactly 60 degrees. And some of you might understand why you get exactly 60 degrees because of that root 3 over 2, which we've seen before. But others may not understand why, and why is not important here. We get a reference angle of 60 degrees, and we move on. You're told in this question that sine is negative, and sine of theta is y over r. So the only way y over r can be negative is if y is negative, and that means the terminal arm lies either in quadrant 3 or in quadrant 4, where the y-coordinate is negative, and you sketch 60 degrees, and I've done a very poor job of sketching 60. That's nowhere near to 60, but it doesn't matter. This sketch is for your help in figuring out how to determine the rotation angle, which is the answer to the question. And in this case, it will be 180 degrees plus the reference angle. In this case, it will be 360 degrees minus the reference angle. So what you're going to get for your two rotation angles, let's see, 180 plus 60 is 240. And 360 minus 60 is 300. So 240 degrees and 300 degrees. I'm just going to, because I want to get out of here, I have some things to do, and I wasn't planning on staying after school for this. I don't mind, but I just want to finish this up. I'm going to give you the answers for this, and then you can follow the procedure that we did in the previous questions to determine the answers and match your answers to see if they match mine. Cosine of theta equals 1/2. You are going to get 60 degrees for theta, and you are also going to get for another angle 300 degrees. What you are going to discover is that the reference angle, when you take the inverse cos of 1/2, will be 60 degrees. You will also discover, by thinking about the fact that cosine is positive, you will discover or realize that you're talking about quadrant 1 and quadrant 4. And when you sketch the reference angle of 60 degrees in quadrant 1, you will get this rotation angle. And when you sketch the reference angle in quadrant 4, you will get this rotation angle. Once again, you are not worrying about number 7. I've taken that out of this unit. The problems that people were working on after this lesson and are, I guess, kind of practice homework problems are on page 98, number 7, 12, 9, and 13. That is different than what's typed out in your handout, so please do what you're looking at on the screen right now. And then there are some supplemental problems attached to the unit handout. If you go to page 25, you can practice 8, 9, and 10. I hope that's been helpful. One final thing. If you were not in class today, we did write a quiz. It's about a 10-minute quiz. You're expected to be in my class Tuesday, which is after the long weekend, at lunch, near the beginning of the lunch, please, so that you can write the quiz. If you don't write the quiz, if you don't show up on Tuesday at lunch, the 0 that's in the mark book is going to stick. It's going to be a 0, and you don't want that. So have a wonderful weekend. For those of you playing basketball, I hope that the tournament's turning out okay for you. And do some math this weekend when you find some time, and we'll see everybody on Tuesday. Take care.